All right, guys, our homework last night was page 153, questions 1 and 2. Any issues with either of those questions? Number 2? Yeah, I was pretty sure we're going to need to go over number 2. So that's good that you mentioned that one. Yeah, we can, absolutely. All right, number 1 and number 2. It says a 55-kilogram female bungee jumper fastens one end of the cord made of elastic material. That's good. Okay, that it's made out of elastic material. She attaches this bungee cord to her ankle and the other end to a bridge. She then jumps off the bridge. As the cord is stretching, it exerts an elastic force directed up on her, which of course it does, right? As it begins to stretch, she slows down. And if she slows down, then clearly there's got to be a force acting upwards in order to slow her down. We want to find her acceleration at the instant the cord exerts an elastic force of 825 upwards on her. So let's draw a free body diagram for this lady. There's a lot of things in this world that I would like to do, and there's a lot of things in this world that I have done. Fun, adventure things. Bungee jumping is not one of those things that I would like to do. Okay, bungee jumping scares me. Not sure why, but it does. Here's the bridge. Here's this lady. We better attach a bungee cord, otherwise she's a goner. Here's the bungee cord. As the bungee cord begins to stretch, it pulls up. We'll call that FB for the force of bungee cord with 825 newtons. Now, there is another force that acts on this lady as well. What other force is that? Yep. Force of gravity. It acts downward, of course, right? Is it going to act downward bigger or smaller than the upward force? Is the force of the bungee cord 825 newtons upward? Is that bigger or smaller than the force of gravity downwards? We don't really know right now, right? We don't really know. Okay? We know that as the bungee cord stretches further and further and further, it pulls harder and harder and harder. At some point, it's going to apply a force that's bigger than the force of gravity. But that's not necessarily going to happen right away. So we're going to draw our force of gravity downwards. We don't know how long to draw that force. We just know that it's a downward force. Don't panic about how long this vector is as compared to this vector, again, because we don't know what its value is. Although we can figure it out, we don't know what it is right now. That's it. Those are the only forces that are acting on this lady. So let's go to our next step. Our next step says what? F net is equal to, always the same step here, right? Always the same step. F net is equal to what, right? FB plus FG, or whatever you're called, the force of the bungee cord, plus FG. Okay, the net force is also equal to what? Totally, the net force is also equal to what, besides FB plus FG? Yep, good. M times A. FB plus FG. The mass of this bungee jumper is 55 kilograms. The acceleration of the bungee jumper, we don't know. We don't know. That's what we're trying to. That's what we're trying to find. FB, the force of the bungee cord, 825 newtons, acting upwards. The force of gravity acting on her, well, she's 55 kilograms, so it's going to be 55 times 9.81. Don't just make it 9.81. Make it mass times 9.81. Is that right, by the way? Have I done everything right there? Good. 9.81 needs to be negative. I don't care whether you put the negative out in front of the 55 or in front of the 9.81, but there's got to be a negative there somewhere. So 825, subtract this, divide it by 55, and when we do that math, we end up getting positive 5.2 meters per second squared. Positive acceleration, what? That doesn't make any sense, does it? She's falling downward. If she's falling down, shouldn't it be a negative acceleration? Tell me what's happening to this woman right now. She's moving downward, but tell me what's happening in a little bit more detail to this woman as she falls downward. The bungee cord is pulling her up, and in fact, it's pulling her up so hard that she's not only moving downward, she's slowing down in the downward direction. Okay, initially when the bungee cord begins to stretch, she's going to move downward she's going to accelerate downward still, speed up downward, but at a rate less than 9.81. She's going to accelerate negative 9.81, negative 7, negative 5, negative 2. She's still accelerating downward. But as the cord stretches even further, she still keeps moving downward, but all of a sudden she now starts slowing downward, which is a positive acceleration, which is exactly what we have right here. So answer this one for me, please. Given that the acceleration is 5.2 meters per second squared, can we now determine which force is bigger, the bungee cord or the force of gravity? If it's an upward acceleration, then the net force must be upward. That must mean which force is bigger? The force of the bungee cord. It's not always bigger, but as it's stretched this far, it's bigger. All right. Okay, B2. During a bungee jump, the velocity of the 55-kilogram woman at the lowest point is 0, and the cord stretches to its maximum. So you guys can picture this, right? She jumps, the cord stretches, 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 stretches. At its furthest stretching point, she stops. And then she starts going back up into the air, right? Even further, even higher. Compare the direction of her acceleration at the lowest point of the jump to the part of the jump where she is accelerating due to gravity. Well, she's free falling. She's got the bungee cord attached, but it's as if she doesn't because the bungee cord isn't taut yet. Okay, it's not stretched yet. So it's as if she's free falling. Which way is the acceleration at this point, up or down? I'll give you a hint. This is an easy question. Which way does she accelerate when the bungee cord isn't pulling on her? Is that it? Downwards. Good. When the bungee cord stretches and stretches and stretches even further and slows her down and actually stops her. By the way, her velocity when she stopped is 0, but her acceleration isn't because her velocity is still changing. She went from a negative velocity to a positive velocity. There's still there's an acceleration there. The question is it an upward or a downward acceleration? As she slows down, moving downwards, that's an upward acceleration. When she stops, she's still accelerating upward, even though she stopped. She's not moving upward, but she's accelerating upward, because in one moment, she's going to be moving upwards. So, compare the direction of acceleration at the lowest point versus when she's accelerating due to gravity. She's accelerating upwards at the lowest point, which is accelerating due to gravity. It's just downwards. And B pretty much just answers the same question, right? At this point, what is the direction of her acceleration? Upwards. Does it make sense why she can be accelerating even when she stopped? She's only stopped for a brief moment, and her velocity is constantly changing. Even when she stopped, her velocity is constantly changing. So if her velocity is changing, then it's got to be an acceleration. It happens to be an upward acceleration because the net force is upward that causes her to slow down. All right. You know what? I don't want to do that one. I want to do this one instead. Oh, that one looks kind of different, kind of ugly. 20-kilogram truck tire lying on a horizontal frictionless surface. That's good. At least there's no friction. If I added a coefficient of friction between the tire and the table, that would make things harder. There's pulleys, pail B and C. B has a mass of 8 kilograms. C has a mass of 6 kilograms. What's the acceleration? Holy cow. What the heck am I going to do here? Well, we got more than one force acting, right? Gravity's acting down on pail B and pail C. So let's draw a three-body diagram. I could call this FG, but then I could call this one FG as well. Let's call it FB, the force of gravity acting on B. The force of gravity acting on C. Should FC be bigger or smaller than FB? Why? Yeah, smaller mass is going to be a smaller force. Let's make it a little bit smaller. There we go. There is, by the way, a force of gravity acting down on this guy, but it's countered by the normal force acting up. So those disappear, right? We don't need to worry about those two forces. These ones aren't counted by a normal force because they're not sitting on a table anywhere. Guys, what I'd like you to do right now is just drop your pens because I'm going to make a mistake as I go through this. I don't want you guys to see if you can catch the mistake, but I don't want you to write anything quite yet in case you don't catch the mistake, because I don't want you to write down the wrong thing. Just follow along and see if you can catch the mistake. All right, we got two forces that don't cancel, or two forces that don't balance. The net force is equal to the sum of the forces that aren't balanced out, FB plus FC. The net force is M times A, and it's also equal to FB plus FC. Remember, when I make a mistake, somebody stop me, please, if you catch it. The mass. By the way, this was 20 kilograms. The mass that I use here is going to be 34 kilograms, the total mass. And it's going to be 34 kilograms because the entire thing is accelerating. That's the whole system. Remember, stop me when I make a mistake. FB, well, that's the force of gravity. But this force of gravity acting only on the 8 kilogram mass. It's downward, right? So we're going to make it a negative value. 8.0 kilograms times negative 9.81 meters per second squared. Plus, well, FC is also a force of gravity, but it's acting only on the 6 kilogram object. So we're going to make it 6.0 times. It's also downward, so we're going to make that negative 9.81 meters per second squared. Let's simplify this a little bit. 34A, let's do some calculations on the right-hand side here. 8 times neg 9.81 plus 6 times neg 9.81. We end up on the right-hand side with negative 137.34. And now we're going to take 137.34 and we're going to divide it by 34. We get negative 4.04, which actually rounds to negative 4.0 meters per second squared. Right? I told you I was going to make a mistake. There is a mistake in there. Bart, what do you think it is? Sorry? You mean when I did the math on the calculator? Well, I did this, and then I pressed equals, right? And then I did this, added that to it, so that's okay. I can do that. Yeah. Okay, so wouldn't I say like 14 times neg 9.81, and then 14 times neg 9.81 again? Oh, okay. So just instead of having FB and FC, let's just call it one force, the force of gravity, and make it 14 times 9.81. Is that what you're saying? Okay. Well, that would actually give me the same answer as I have right here, right? 8 times neg 9.81 plus 6 times neg 9.81, 14 times neg 9.81, same thing. Same thing numerically. Allie? Well, it's downward though, right? Allie says FC isn't negative 9.81, but it's downward here, right? FB is downward, FC is downward, right? Oh, wait. So you're saying that FB and FC like oppose each other? Yeah. They do. That's like a tug of war, right? Is that what you're going to say? Yeah. FB is pulling one way, FC is pulling another way. They happen to both be pulling downward, but they're still opposing each other, right? So one of these forces has to be a positive value. It doesn't really matter which one you make positive, okay? But you're going to see in a second which one it probably makes more sense to make positive. Here's what I want to do. I want to redraw this. And this is what I like to do every time I have a problem involving pulleys like this. Let's pretend that this 8 kilogram mass is horizontal. I pull it up horizontal like this. And then the 6 kilogram mass, I pull up horizontal like this. If I do that, we've got an 8, we've got a 20, we've got a 6, we've got a force of B acting to the left. And if I pull the 6 kilogram up in the same way, I've got a force of C acting to the right. So now what I'm going to do is take a look at what I just did mathematically with my new free body diagram, not with my old one. Still the same forces, FB plus FC. The total mass here, still 34 kilograms. That's good. You always put the total mass in there. FB plus FC, good. FB is negative because it's to the left. FC is positive because it's to the right. Now, it's not really to the right. It's downward. But this helps us to visualize exactly what Ali said, and that is that the forces oppose each other. You don't have to redraw it like I just did. I won't mark it wrong if you don't redraw it like I just did. But in my experience, it tends to lead to less mistakes if you redraw it like I just did. You tend to mess up on the negatives and positives less often if you redraw it like I just did. Okay, so we got to change this then. We got to change this whole thing on the right-hand side. Let's say now 8 times neg 9.81. Let's press equals. And then let's add, we can still add it like this, right, on our calculators, as long as we use brackets. 6 times positive 9.81. That gives us negative 19.62. 34, 19.62. Let's take the 34 over by dividing. So neg 19.62 divided by 34 gives me an answer of negative 0.58. And that's my correct answer. I know Ali and Lewis were both caught the fact that 6 times 9.81 should be a positive value. Anybody else thinking that? I'm just kind of afraid to speak up just in case you were wrong. Yeah, good. Good. Now you can write it if you want. All right, let's take a look at a couple practice problems on 157. You can see that the first question is involving 3.11, example 3.11, the one that we just did. So what I've done is copied over the diagram for 3.11, but this time we're changing the masses. So pail B is going to be 12 kilograms. Pail B is 12 kilograms. The tire is still 20 kilograms, and pail C is still 6 kilograms. So we're solving this the same way. We're just using different numbers here. Let's give that a shot, and then in a few minutes we'll go over it as a class if we need to, okay? All right, everyone, let's take a look at number 2. We're back to our example, again, 3.11. We're going to stretch it out that it looks like this. We're back to having 8 kilograms here for object B, okay, with a force of gravity acting on object B that's not really to the left, but pretend it's to the left. Our tire now is 15 kilograms instead of 20 kilograms. Pail C is still going to be 6 kilograms. And we've got a force acting on C that's to the right. Not really to the right, it's really downwards, but we're pretending it's to the right. The force of B would be gravity, force of C would be gravity. Okay, the net force, by the way, there would be a force of gravity acting down on this, but there's a normal force acting up on this, and it cancels. So somebody asked me yesterday, if we don't draw on that force of gravity on when it cancels out with a normal force where we lose marks? No, I won't. I won't take marks off. But we really should draw it in, okay, just for completeness. We're going to say the net force here is equal to the sum of the forces. That's going to be FB plus FC. We don't have to worry about FG and FN here because they've canceled. Fnet is also equal to M times A. FB plus FC. The mass here, what mass do I use? 8, 15, 6, or some sort of combination of 8, 15, and 6? Seth, what do you get there for the mass in number 2? Yeah. Okay. 29. 8 plus 15 plus 6 is 29. We got to use the entire mass here. Use the entire mass. Okay, let's be focused, everyone, okay? Let's focus on what we're doing here, everyone. FB is going to be, it's going to be 8 times negative 9.81 because it's to the left. FC is going to be 6 times positive 9.81 because it's to the right. Even though they're both really downwards, we're drawing them to the left and right just to help us to visualize what should be negative and what should be positive. So we get 29 times A is equal to negative 19.62 when we do the math on the right-hand side. And then A is negative 19.62 divided by 29, which is negative 0.68. Now somebody, I can't remember who it was, asked me earlier on, I get 0.68. It says negative, sorry, I get negative 0.68. They don't say negative there. Do they say negative? Well, kind of, actually. Kind of. We know that this system is accelerating to the left, right? That means that pale B, that means that the acceleration of the system will be negative. Pale B accelerates downward. The tire accelerates to the left. And pale C actually accelerates which way? Upward, right? The system accelerates to the left, but part of that system accelerates upward. Okay? You don't need to worry about that, though. If you leave it as negative 0.68, I'd accept that as your answer. You good there? Here's a question that I want you to work on for homework tonight. You got 3 objects, just like we had in the last couple of questions that we did. Object A is 10 kilograms, object B is 5 kilograms, object C is 30 kilograms. We're going to assume that when we let this go, it's going to move. Therefore, when friction acts between object B and the surface, there will be kinetic friction. The coefficient of kinetic friction there between these two surfaces is 0.20. I want you to go through this and find the acceleration of the system. Okay, real similar to what you just did for the last 3 questions, but this time we're dealing with friction in here as well. I want to see if you can put that into the mix and still get this right. Okay? You can start work on this now, and then, as I say, finish it up for homework tonight, please.